So the Pascagoula FCC is on the Gulf Coast of Mississippi, built in the early 60s, Model 4 unit. Original capacity was around 66,000 total. Majority of that, or close to half, was recycle feed before Z-Lite catalyst. Big revamp in 91, went to slide valve control, and then the next major revamp was in 2006. So that put the the rebuild for the normal turnaround cycle in 2021. So in preparation for the 21 turnaround, we were thinking about what could we do. So our focus, for those of you that are not FCC people, is on the Regenerator. So the two main vessels here is where we circulate the catalyst back and forth between regeneration and the reaction. This unit has a circulating inventory of around 550 tons. We circulate about 50 tons per minute, just to give you some scale. This Regenerator vessel that we'll be talking about, around 40 feet in diameter, and it has 11 pairs of cyclones, and there's 22 cyclones total. And it's what we call a side-by-side unit, which is creates some challenges. Part of why we were looking at opportunities. This isn't what would be considered a modern design, so it's typically circulation limited because of these angled standpipes. Originally, these were U-bends without slide valve control. A more modern unit, the reactor is typically above the Regenerator, which lends itself to higher circulation rates. So if the feed rates were pushing, this unit's considered cat to oil circulation limited. So the things that we were wanting to look at improving or not make worse specifically, environmental performance is always a concern. So better mixing of air and catalyst result in lower CO, better afterburn, lower combustion promoter usage. Catalyst losses, this unit had some sensitivities to circulation and carryover. So, some of it is because of internal geometry. It had mitered dip legs, which those of you know the dip legs, is where the catalyst comes out of the cyclone. We suspected those were part of our problem. So we were looking at ways to rearrange the internals to get rid of those miters and just have straight dip legs. So pretty simple, straightforward thing. But when you're trying to cram that much equipment into a small space, you end up with compromises. So anything we could do to improve circulation. Also, the way the cyclones were arranged, every time we went in these since the 2006 revamp, we noticed the center cyclones in the middle. There were two pairs situated in the center. They always had more erosion than the external pairs. It's like, hey, what can we do to those? Because every time we had to go in, there's 2 or 3 days of extra maintenance just to work on those cyclones, where the ones on the perimeter weren't seeing that erosion. So that was a question, how do we make that better and eliminate that erosion? And again, the overall goal was, it's not really broke, but so don't fix it, don't make it worse. So there's a lot of people supporting this unit that were, like, hey, this is really good. The 2006 revamp was a huge upgrade from what they had before. And so there was a lot of anxiety around, don't make it too good. If you know what that means in the refining world. So this is the project timeline. The main reason for showing the timeline is it takes a long time to get one of these projects done. You need a steward that can carry it all the way through. So for those of you in leadership positions that have an opportunity to influence who's assigned to your technology, keeping people with a technology, it pays out. I was involved from this unit since 2008 until now. And so as I've moved different jobs, I've stayed close to the unit and had an opportunity to influence this work. So you can see, whoops, wrong button, sorry. We first started talking with CPFD in 2003, knowing that the turnaround wasn't until 21, where we would be thinking about this work. After we had a shutdown in 15, the planned turnaround, or in 16, based on the inspections, we decided, hey, we're going to replace the entire Regenerator head. So this is our opportunity to make a big change to the unit. Kicked off the project with CPFD in 2018, finished the modeling around 19. COVID gave us a 1-year delay. We executed it in 22, and here we are today, about 2 years later, looking at the results.
And we're going to hand off and talk about the CFD and what it means at the refinery. So this is going to be a little bit of a back and forth. But when you look at, okay, a project in 2018, how relevant is this? That's 6-year-old code. I can't do math. 2018, 2024, yes, it's 6 years. I'm in a commercial role these days. So what's different? So a lot of things have changed over that time. The simulation speed, we came out with a GPU version in 2014. By 2022, the 2014 was somewhere between 2 and 6 times faster than CPU or than serial. By time 2022 comes around, did some new benchmarks, that's between 50 and 100 times faster. So the code's somewhere in the middle. Things are a lot faster. We've come out with multi-GPUs since that. And as a result, what's happening is the simulations today, the resolution, the complexity, what we really put in and how we resolve things is much different. There's also been a proliferation of FCCU simulation. By 2016, when we chatted again, and to 2018, really the first papers were coming out, not on it can be done, but people actually doing it, and the first case studies of, okay, here's an actual regenerator, perhaps anonymously presented with results. Now that's far more common. And the code has changed. Things like a particle going into a cyclone now comes back, like in an FCCU, or with a grade efficiency curve. Particles leaving a standpipe, there's boundary conditions that mimic the slide valve and sort of a max circulation rate, which were a lot of hoops to go through back in those days. And even the use of empirical models, drag and so forth. So a lot's changed, but there's certainly things that are quite the same.
That's right. So the common ground is we still have turnaround cycles, or we're not getting away from those. You have to coordinate with a lot of stakeholders to get approval, get buy-in. You know, that's part of the value, and the modeling is very rigorous. So it's not just my opinion. You're getting, you know, a lot of involvement from outside experts. We involve PSRI in addition to CPFD as part of the stakeholder engagement on the changes we were considering, and risk reduction, right? You only get one shot at doing this. If you come out of a turnaround and things are bad, you're stuck with it for 5 years, 6 years. So.
Okay, I'll take a few slides to talk through the model itself. So what this was, we limited the domain to the regenerator itself. The major components were all included, so things like the cyclones, that's going to be, you know, up here. 22 of them, as Rob mentioned, some mitered bends, the spent catalyst, the spent catalyst distributor, the air grid, the top here of the regenerated catalyst withdrawal. Some smaller components, we try to include the effects of them, either with subgrid baffles or other boundary conditions. So there was a burp tube on the standpipe that came up. We handled that with a baffle. Probably didn't affect the simulation results, but really helped visualize, okay, as we're moving around cyclones and dip legs and mitered, and you have this Tetris puzzle of how to fit it all in there, what are the clearances and what are the interferences? Other things did matter more. So the torch oil nozzles, the fluffing rings, these were put in, but as point source boundary conditions. And then we didn't handle the whole catalyst withdrawal pipe, handled with a boundary condition treatment. And then we took the information from the refinery, from Rob and the team sending over, so the DCS data for the operating conditions, boundary conditions, the ECAT particle size distribution, so the full particle size distribution. And a lot of these things are not directly measured. They come back out of a material and energy balance. So we put those boundary conditions in. It was run thermal and reacting. So we took sort of some standard reactions from the open literature that we use quite commonly. There's the combustion of the solid components, the coke, carbon and hydrogen in the coke. You'll also going to find here 2 gas phase reactions. Both look the same. It's the carbon monoxide combusting to make CO2. But there's 2 of them there. One is homogeneous, so you just in the presence of the gas phase, once the temperature's reached, the reaction's a function of temperature. The other is catalyzed. So this is looking like the same reaction, but at a different rate. So to capture the effect of the combustion promoter that was used. And this animation, maybe I'll click again and it'll play. No. Let's do this again.
There it went. Just
Thank you, Matt. Okay. If this is not going to have animations, this is going to be an interesting talk. But I will start talking. He's doing with the hands up, but that's okay. I will keep going, and if he swaps it out, we're good. So we always have a baseline that compares against, whenever possible. You know, what's good, what's bad in a unit that's been around for, what year, 50 something, did you say?
Yeah, 65.
65. So what we look at is not just one component, but a lot of details of the fluidization. So on the left, I'm going to just walk through left to right. These are simple, it would be a transient animation, but what you're seeing is instantaneous results here, going through a single slice of the model for visualization. And on the left, we're seeing the catalyst volume fraction. So you're starting to see things like the dense bed, sort of a splash zone, a dilute phase. This is taken further out in the calculation. Next, we're seeing the temperatures. Now, this is in a more narrow range between 12 and 1400 Fahrenheit. But you're definitely seeing a profile, and as animation would be going, you'd see the evolution of all this, how this is beginning to form this cool zone over time. We'll look into why that is in a moment. Then we're looking at the oxygen. It is a full burn unit, so it should be utilizing all that oxygen, but there's patterns in how that comes through. Next in the green is the CO, and then the CO2. So we're looking at the evolution of the gaseous species. But as we look at this instantaneous, it's often helpful, and we'll have this animation after the fact, but to look at a time average sense. So looking at the time average, let's start in the middle. The conclusions were made that, okay, there tends to be a left to right from this view asymmetry of the temperature. So that's one thing that's clear. You have, and it's very logical, the cooler spent catalyst is coming in, and it seems to be tied to that zone where things are cooler. Looking on the left now, that is directly impacting the CO. So rather than going fully from the CO to the CO2, which is a strong function of temperature, where you have the cooler temperature, you're actually more in partial burn on the left side, so you have high CO. And to have some is not an issue. What you want is it combusted away generally before it hits the cyclones and leaves the regenerator. And what's causing this? You certainly have the cooler spent cat coming on the one side, but it's not just the fact that it comes in on one side. The third view here is looking at the vertical gas flux, or if you divide by density, you have essentially a superficial velocity, or velocity. And what you're seeing here is, and at least in this slice, you have a high upward velocity where you have not just the air from the air grid, and then the lift air that is pneumatically conveying the spent catalyst in, but somewhat coming together, being pinched by some of the obstructions, and having a very high flux out in that area. So the spent catalyst that's coming in seems to be coming out very quickly rather than combusting in the bed. And here we have an animation, which is a movie. Thank you, Matt. Let's look at why. So in Barracuda, it's very easy to take simulation results and say, show me just some of the particles. And in this case, we're looking at just the spent cat that has been in the unit for less than 5 seconds in the simulation. So we're not showing all of it. All of it is in the simulation, but we're only showing some of it. Here we have it colored on the left by the mass fraction of the coke. Comes in just under 1% coke on catalyst. On the right, we're showing the same particles, but colored by temperature. And something really interesting is observed. Comes in cool, and it takes, within 5 seconds, a lot of these raise their temperature at least 100 degrees or more. When that happens, the coke on catalyst is coming down. So it takes just a few seconds to warm up and combust. By that time, it's already being swept out. And so this cooler zone that's leading to the CO is largely impacted by the spent catalyst distribution. So then what to do about it? Now that we have a baseline model, what was your thinking at this point?
So once we had the baseline, we start considering, okay, how do we make it better and not break it at the same time? So apologize, all the case drawings are the same, so focus on the descriptions. So base case, you have 9 pairs around the perimeter, 2 in the center. So like the first thing we want to do, let's get rid of those cyclones in the middle. They're the problem, they're eroding. It has to be better without those. So we want to run that case for sure. And, so we made sure they would all fit. Once they fit, we committed to that case. The third case, okay, what would it be like with just one center pair? Mm-hmm. And that's really where we started. It was down the road a little bit, case 4 and 5. Once we had the first 3 cases running, we did some iterations of the first 3 with, we made some modifications to the spent cat distributor to see if we could better spread the catalyst across, leaving with no center cyclones. And then we did the 1 center pair, but turned down, so that's reducing the feed and the air rate, just to make sure when we're running, because that happens in a refinery, right? You can't run wide open all the time. What happens when we have to back the unit down, make sure nothing weird happens there. And also it was just a chance to test the rigor of the model to make nothing drastically change, to build confidence in the model across a wide range of scenarios. Because for the bulk of our team, we'd never done any modeling this rigorous. So, to be honest, there's still some naysayers in the group like, hey, this modeling, the pictures are real pretty, but do they really predict what we're going to see in the unit? And the last one, we messed around. We left the center pair, but we plugged some of the nozzles in the air distribution grid, just because where the spent cat distributor comes across the grid, there's some interference. Like, well, is there anything weird going on there? Do we need to move some air around and make some of those changes? So there's another chance to test the rigor of some hardware changes. And that's where we've that's good enough. But the neat thing for me, if you tried to do these in real time without modeling, it could take 50 years to do these iterations, to make a change, run 5 years, get the data, and go back and compare the results. So that's looking back at this project, but we did that in 18 months with modeling. So I thought that's pretty neat.
All right, let's talk through some of these iterations. And we're showing more cases. We can fit about 5 across. Really the focus here is on the first 3. This is the baseline. What happens if we eliminate the center cyclones entirely? What if we have another? And then we're going to show there's some more other parametrics, and there actually were a lot more cases that couldn't neatly fit on this slide to just get you a feel for the types of things we looked at. So looking at, first of all, just the bed densities. In all cases, you have about the same bed elevation, but this pathway for the air to come out and sweep catalyst along with it that we saw in the base case, not fully eliminated, but much higher densities across the cross-section in cases 2 and 3. So the first thing is both of those looked like an improvement at this point. Then we started looking at, okay, what about that gas flux that's pulling it out? So this strong channel in case 1 mitigated in both 2 and 3. Still some elements of it. It's still not 100% uniform, but far more uniform. Maybe case 2 is doing a little bit better at this point. And again, testing on some of the other alternatives that were under consideration. Looking at the temperature effects, and here's where you started seeing notable differences. In case 1, this left to right cool zone, now you have just a much smaller cool zone right where the spent catalyst is coming in. Again, little differences in case 2 and 3. Turn downs, obviously significant differences. Looking at the time average CO. So the net effect of this in terms of the CO, this persistent CO all the way. Of course, you still have some where you're going to have cooler. It's going to take some, it's going to produce more of that CO, or that CO is going to take more time to combust. But not nearly as intense and not persisting, and this is the key, not persisting all the way up to the cyclone elevations, nearly the way it was before. So we looked at some of that sort of slices and average data. Now, you always got to be careful what you show. I can probably pick any nice one slice to make a point I want to do. They don't call CFD colorful fluid dynamics for nothing. You got to make sure you're doing some. So one of the things, and this is just a subset. We had 150 page of analysis. Probably we're not putting that through here. We're going to ignore this timer because we just got 2 talks today, and this is exciting to me. Don't listen to that when I'm the MC tomorrow. So going through, we start to see, okay, what's happening at the cross section as it's going up, and you'll see all of them have some cool zone down here. So as this is coming up right around the spent catalyst, of course you do, the cooler spent cat's coming in. But look how quickly it dissipates in the other cases. So this is just one example of how we're looking through the 3D, through the elevation. We're also doing quantitative analysis. So you can take all the flow into all the cyclones, sum them up, and we computed that then for the relative CO entering the cyclones. And this is in a relative basis. So compared to the baseline, if we say that's 100%, what you see is both cases 2 and 3 do a significant job of reducing that CO before it even hits the cyclones. Again, as the images were implying, case 2 is probably a little bit better, but both are doing a very significant reduction. But it wasn't just one aspect we're looking at. We weren't just looking at, okay, what's CO doing? You know, there's entrainment, there's catalyst losses. What about that? So let's look at just one other criteria, and there were many that we considered. Let's look at the entrainment of the cyclones with the hypothesis that catalyst losses will probably go somewhat with cyclone entrainment, which is not a measured quantity. And here's what we found. So here's some relative entrainment into case 1. Case 3 is about the same. Case 2 is saying it's going to significantly increase the entrainment of the cyclones. And so all of a sudden, case 2, which is looking best, case 3 is looking pretty good at this point. And so this is just part of the journey. There's a lot of other things we looked at. One way we often do look at NOx is rather than complex mechanisms, we often found historically, and you can find this in a paper that Jim Parker, Sam Clark wrote with Ray Fletcher at the 2016 AFPM meeting, looking at flow uniformity, sort of a measure across the cross-section that you can easily dump the data from Barracuda and analyze. And this uniformity index from case 1, basically, if you had perfect flow where every part of the cross-section was delivering the same average flow, you're going to have 100% uniformity. Never happens. You have air coming in on one side, you have complex geometry, but look at what happened. Coming from case 1 to case 2 and 3, we're seeing this increase in the uniformity, and invariably, when you have more uniformity, you have more uniform temperatures, as you were seeing, and the NOx is greatly reduced when you have uniform temperatures. So that's sort of an indirect metric, simple metric we use to say, is there any surprises we're expecting on NOx? And there were a lot of other assessments. I won't go through them all. There were other things on the gas particle hydrodynamics, on the heat transfer, the temperatures, on the reactions, the gas species. Looked at erosion and relative differences between the cases. Looked at the mixing. What's the spent catalyst doing coming right out? Not just in terms of sweeping out, but radially, and how's that going across the unit? Is it impacting any structures? The coke unregenerated catalyst with Barracuda, you can dump all the raw particle data. And that's easier now too, because you can actually have it tracking out at the boundary condition. And plot that and look for a salt and pepper where you might have a bypass of the catalyst down the regenerated catalyst standpipe. The loadings, not just total entrainment to the cyclones, but by cyclone. How uniform is that? And even the PSD going to cyclones, we looked at that. Rob mentioned various nozzle plugging patterns. And made a decision. I didn't, you guys did. Why don't you talk?
That's right. So we picked case 3. As bad as we wanted to get rid of the center pair, there were several reasons. The risk of catalyst entrainment said we're not going there. We'll go halfway. We'll go from 2 to 1. We also ended up adding 2 feet to the total regenerator height because looking at the cyclone design to get the right cyclone geometry, we needed a little bit more space. So that was an easy thing to do to ask for. It was a lot of work in the field. But that is a change that wasn't modeled. We discussed it with Peter, discussed it with PSRI. TDH is a good thing for cyclones, so that didn't get modeled. So a lot of collaboration between different groups to get to that decision. And then this is a list of different parameters we analyze. So the first one, so these are the trend. So this is a 6-year trend of the ESP fines before and after. So the after is right here. This is the 2021 or 22 turnaround in January 22, and you see a big change in fines. So the variation in the fines decreased dramatically, and much higher percentage of the fines is 20 microns or less now. So that was a win. So now we're capturing more in the Regenerator and those than we were before, which is consistent with the modeling results. Look at the 0 to 40, same story on the 0 to 40. Way less variation, and a much higher percentage is less than 40 microns. So just more evidence. If you look at the full range of particle size distribution, it all says the same thing. Less variation on what's happening in the regen. It'd be interesting to get feedback when we get into the Q&A. Was it the miter dip legs? Is it the arrangement? But all good news. APS as well. The APS decreased, which is consistent with a higher capture rate on the Regenerator side. And then the ECAT, 0 to 40, what's in the circulating inventory, the 0 to 40 went up. This was important because better 0 to 40 is better circulation for a unit that's circulation constrained. This gives us more stability, which turns into operator confidence, where you don't have erratic slide valve DPs to push those limits, because we're always having to push the crews to challenge those limits to get as much as we can out of the unit. Slurry fines, this is the squeezing of the balloon. We squeeze the Regenerator, so where are those fines going to show up? They're still going to leave. We didn't do anything to the reactor, and we expected this, but our reactor side losses were already very low for industry standards. If you move more solids to the slurry side, you're going to be concerned about erosion, but we're already pretty much best in class there compared to units that have high erosion issues. So that was one of the trade-offs we were willing to go after, but you do see not a huge change in the 0 to 40, but the 20 and the 0 to and the 1 micron. So that means more larger particles are shifting to the reactor side. And then the slurry APS, significant step change here as a result of that move. These trends aren't for you to analyze. Really just wanted to show you the amount of variation in our unit. These are all the cat losses, but the top line is our biweekly average of fresh cat addition. The unit post turnaround, because of economic reasons, availability of feed, we went through more ups and downs than we had prior to that, which is reflected in the variation. But overall, fresh cat adds increased a little bit. So even with the increase in fresh catalyst addition, the regen losses still came down, because with that fresh addition, you're getting more fines that you lose pretty much immediately. But even with that slightly increase in fresh, the regen losses went down. You can see the bump in the reactor losses slightly, but the variation and the amount of total cat losses, both of those decreased slightly. And that's reflected in the table here. That's the numbers. I didn't want to hide the variation in the averages, so I gave you both, because the average never happens. You can hide a lot in the average. The right button. So environmental performance. CO was the big win. These spikes were due to feed running at low regen temperatures, makes higher CO. But overall, significant decrease in CO, which is what we were expecting by the improved distribution and getting rid of that bias towards the spent cat inlet side of the Regenerator. The benefits there, you get to use less promoter, run lower dense bed temperatures. And then NOx, you could argue if NOx changed or not. NOx is more, of a function of feed nitrogen typically, but we didn't make it worse, which is a win. So our conclusions, it minimized our turnaround risk, to make a change of this size for what's at stake. We got to analyze a lot of options in a short period of time. And all the changes were good. so far so good on environmental, losses are better, and we expect to see an impact on the erosion of these cyclones, so hopefully that turns into less maintenance for the next turnaround. And that's, we're ready for questions.
Well, thank you, guys. Let's thank our speakers.